Okay, so we'll go over the final topic quickly because it's just providing some prospect of the future, and then we'll start the presentation starting from today. So as I said, if you present 2 papers, okay, you will have full credit. If you present just 1 paper, you have half credit. So you need to present at least 2 papers. Okay, and we don't have much time, so I'm trying to go over this quickly. So this is the slide that I gave to Samsung a few years ago, because at the time Samsung was considering processor design, because the computing industry is growing. But because the head of the research center at Samsung moved to other university, actually the project was cancelled. But anyhow, this is somewhat summary of what we have discussed and what will be the future of processor. Okay, so most of the stuff I think you already know. So let me go over this slide, which I think I have explained before. So processor execution time can be expressed by the 3 components. If you want to improve computer performance, you have to improve in 3 aspects. Okay, the first factor is called program size. You have to reduce the program size. It means it depends on the instruction set architecture. For CISC, you can produce smaller program, but for RISC, you can make machine simpler, but the program tends to be larger because you have limited number of instructions. Okay, so if you compare 2 different machines, same clock speed, same IPC, then you should choose CISC machine because it gives more compact program. Small program means it requires less number of instructions to execute to complete the program. Okay, so that's the program size. The second factor is called CPI, cycles per instruction. For each instruction, how many cycles it takes. Okay, and the inverse is called IPC, how many instructions per cycle. The third factor is clock cycle time. So you have to reduce the clock cycle time to improve program performance. You have to reduce CPI, or inversely you have to increase IPC. Okay, and you have to reduce the program size. If you multiply all this will result in execution time per program. For program, how long does it take? So number of instruction divided by number of instruction divided by program. Okay, or number of instructions times instructions cycles divided by instruction times second per clock cycle. So clock cycle cancel out, instruction cancel out, and so on. So it's actually second. How long does it take? Second for each program. So to increase performance, you have to decrease program size. It depends on your instruction set architecture, and it depends on your compilers. You have to decrease CPI or increase IPC. Okay, it depends on how much you can exploit in your processor for this kind of parallelism, which is called instruction level parallelism. So how many instructions per cycle you can commit, okay, for out of order pipeline, and how much you can reduce the clock cycle time. Inversely, how much you can improve your clock speed. Okay, it depends on the pipelining or semiconductor technology. So this was the trend. So we already know we have improved about 42 times in the terms of clock speed, and IPC about twice in this about 10-year period. But it saturates. Starting from 2002, this processor performance curve was reduced from 51% per year, which we enjoy this Moore's law, about 20-year period. But starting from 2002, this is about 20% per year. This mainly comes from semiconductor process technology, not from architectural innovation. This is single program performance. If you want to improve the performance of single program execution time, it's not easy. Okay, it takes a while. But in terms of throughput, how in terms of total number of instructions per cycle is much higher due to multi-threading and also due to multi-processor, multi-core technology. So even though single program cannot run much faster, multiple programs can run simultaneously every cycle, which will increase IPC, the throughput, not single program performance nowadays. Okay? So we have reviewed this superscalar out-of-order pipeline structure, and as you have discussed, each stage we have this bottleneck. So fetch stage, to implement wide issue superscalar, you have to provide as many number of instructions. Maybe if you want to implement 5 IPC, right, you need to support maybe 7 or 10 instructions front end should to provide so the back end can consume, right? Because some of them you have to cancel, right? But providing this high bandwidth instruction fetch was not easy, and one technique we studied was trace cache. Okay, and renaming, decoding is also complex, but the renaming stage, the complexity is quadratic in terms of more than it's actually quadratic in terms of issue width, right? And wake up and selection logic is more than quadratic. It depends on the instruction size, and it also depends on the instruction issue width. So it's composite. So actually, this is quite complex for 4 issue or less. But as you increase issue is more, this bypass logic complexity and this wire delay becomes the bottleneck. Okay? Wire delays, and because of this wire delay, register access also takes more than one cycle. You cannot read register file in a single cycle, as was shown in Itanium processor. Itanium, the original design was 8-stage pipeline when I work on, but after 1 year I spent time on there. The designers concluded that we cannot implement register read in a single cycle, so we add actually 2 stage to the pipeline. So register read takes 2 cycles, write takes 2 cycles, so it becomes 10-stage pipeline. Okay, because of this wire delay. And overall, superscalar processor is not scalable in terms of issue width. You want to improve performance and increase IPC, but as you increase your issue width, hardware complexity become more and more complex, and the performance gain you can achieve is smaller and smaller. Okay? So we have reviewed all these limits of instruction level parallelism. So even though you implement very high issue superscalar backend, right? Another problem is the application program doesn't have that much parallelism to exploit. Okay? So okay, so as you increase this x-axis is actually issue rate, and this is the performance. You want linear performance curve, that is the ideal performance you want to achieve by increasing the issue width in superscalar. But the hardware complexity grows, and the power is actually proportional to the hardware complexity. And the actual performance you can achieve is less and less as you increase more issue width because of dependency and other reasons. So there is an increasing gap between hardware complexity and actual real performance you can achieve. And the other issue was this power. Power consumption was too big. Okay? So increasing clock rate is also not energy efficient because it increases transistor switching, and faster clock requires deeper pipeline. Pipelining has overhead. It decreases your IPC because you have to cancel more instructions in the pipeline whenever you have misprediction or exception. And The other problem, this is quite significant. Problem is power consumption. It already reached the power limit. So 1.6 gigahertz Itinium-2, when it was announced, it consumed 130 watts of power, and that's the power budget maximum. And the other problem is temperature problem. Pentium power density passed that of hot plate in 1998, and it passed a nuclear reactor in 2005. At the same speed, if you increase the clocking speed, the same speed, it will pass the lock and nozzle in 2010. That's why we don't see any processor with more than 3 gigahertz processor nowadays, right? So this trend was starting from year 2000. We have seen 3 gigahertz Pentium 4, but still we are seeing 3 gigahertz i7 because of this power problem. And the other thing I didn't note here is the reliability issue. If you increase your temperature 10 degrees, the system reliability goes down by half, which means there is more errors, like bit errors, parity errors. Okay, so system is not reliable, so you need to compensate the cache and DRAM with ECC, which means more memory, right? More cost, more complexity. And still you cannot achieve the same level of reliability in the system. So you have to control the temperature, you have to control the power, so you can improve your clock speed. Okay? And the solution was multi-threading, which we have discussed, right? So instead of existing superscalar, they have this vertical waist and also horizontal waist. Even this is 4 issue, you can issue only 2 instructions, right? But by having SMT, you can use multiple threads, and every cycle you can issue instruction from multiple threads. So you can target this horizontal waist and vertical waist at the same time and improve processor utilization, improve overall IPC, even though you cannot improve single program performance. Okay? So this is the result from IBM Power 5. They have this SMT, 2 threads active. So overall, if you run 2 identical copies of the same application in SMT mode, right, multi-threading mode, then for integer benchmark, you can improve performance by 23%. And for floating point, about 16%. So you have more improvement in integer application, which means PC application, because there is more bubbles. And you can target these bubbles with other thread instruction issue. Okay? So that's one solution. The other solution is multi-core. So it's single chip multi-processing. The idea is quite simple. It's easy to design and easy to verify functionally. You just have the same core, you can replicate. You can reuse the existing designs. And the other advantage is it actually gives better performance in terms of power consumption. Because as we have discussed, dynamic power consumption can be expressed as CV square F. But if you decrease your voltage, you can also decrease your frequency. Okay? So compared to a single maximum frequency processor, if you have dual core with operating at half frequency, okay, it will produce the same result in terms of total IPC, okay, because full frequency versus half frequency, but twice. But the idea is you can reduce the power by reducing the frequency. So actually, overall, dynamic power consumption reduced by 1/4. Okay, even though you implement same performance with multi-core. Okay, that's the perfect match for this bottleneck of power consumption and also performance. So people move to multi-core technology, and I mentioned here, and also the other issue was if you increase the power consumption, if you increase the temperature, packaging and cooling cost increase substantially. Chip temperature must be limited to avoid reliability issue, and leakage power consumption. If increase temperature, it increase static power consumption also. Leakage power means static power consumption, okay, without switching. Okay. So overall, you can substantially improve throughput, okay, with minor degradation in single program performance, because you need to share caches and memory, and there are resource conflicts. So maybe you need to sacrifice single program performance a little bit, but overall you improve throughput substantially, and you can reduce the power consumption also. Okay, and this is good for multi-programming workloads and multi-threaded applications, and you can enjoy the benefit of multi-core. Okay, so Intel moved to multi-core. This was the example for Intel Core 2 quad processor. So in its design, it has two 64-bit dual cores in a single package. This is somewhat old, about 5 years old, a quad-core processor. And for this core, it's called Core 2 pipeline. It's derived from Pentium 4, not from Pentium 4, because Pentium 4 is too much deeply pipelined. It can increase the clock speed, but we don't need that much clock speed, right? Higher clock speed means high power consumption. So instead, the actual pipeline was derived from Pentium 4, which was 10-stage out-of-order pipeline. They improved from 10 stage to 14 stage, and from 3 issue to 4 issue out-of-order pipeline. So they actually reduced the power to about 65 watts, but more performance compared to Pentium 2. Pentium D processor is dual core, but it's more like Pentium 4 version of multi-core, but it was not efficient for multi-core, so they changed the microarchitecture. Okay, and another example is Spark from Sun Microsystem. This was T2. In a single chip, it has 8 cores. Each core runs at 1.4 gigahertz, and each core is 8-way multi-threading. So each core has 8 program counter. Okay, you have actually 8 cores, so you have 64 threads or 64 program counters running every cycle. So this is for server application, which has a lot of this. You can create a thread and can match all these requests coming up from the remote client. Okay, use 65 nanometer process, so it's not aggressive semiconductor process technology, but it's actually exploit TLP substantially. Okay, and they use in-order pipeline, 2 issue, okay, and so on. So here you have this 8 processor cores, and you have full crossbar network because they avoid this bus technology. It's not scalable with multi-core. So crossbars and L2, and crossbar is also not scalable, but it's actually very expensive design. And memory chips are already integrated into the CPU chip, which is now a trend in i7. Okay, this technology moved to PC, but this is for servers. Okay, and T3 was the code name. The project name was called Victoria 4, and this T2 was called Niagara. And this Victoria 4 was already implemented, and it actually had 16 cores, and each core is 8-way multi-threaded. So Sun's T3 processor, you have 16 core and 128 program counter running every cycle. 128 threads running every cycle. That's the trend. And even embedded processors such as ARM also implement this multi-core technology. So you can see Samsung or Galaxy or iPhone, they use all this quad-core or dual-core technology for their processor embedded in the SoC. Okay, A4, A5 chips are SoC, not processor itself. It includes processor, but it has other peripherals also. Okay, so this is Cortex A9 multi-core based on 32-bit ARM instruction version set architecture. Each core is 2-issue, 8-stage out-of-order pipeline. So it's more similar to more high-performance processors used in PCs. Okay, so you have 4 cores. Okay, 4 cores in this MP core, and they extend this to this is A9. They have A50 and so on. Okay, more advanced processor nowadays. Okay, so it's moving to many cores. Okay, starting from 2002, IBM starts from Power 4 with dual core, and Pentium 4 at the time was a single core, but IBM Cell, which was used in Sony PlayStation, was 9 core with 8 normal, they called SPP or something like that, parallel processing engine for their graphics and game application, and they have another host processor, so it's totally 9 cores. And T1 Sun Ultra Spark was 8 cores, and Intel Pentium D was dual core, and then Intel moved to quad core, and also they built some experimental machine called Teraflops with 80 cores. This is not shared memory, this is distributed memory multiprocessor, which we have discussed what is distributed memory, and so on. Victoria 4, 16 cores, and so on. And there are other spectrum which I didn't show here, such as some from graphic processor. They have many cores nowadays, maybe more than 1,000 cores nowadays. So it's moving to many cores. Okay, so Intel also built some many cores nowadays. So I asked some of my students to present this new processor from Intel and NVIDIA, so we can discuss what's the trend in this many core also. Okay, and all the others are my guess, my projection at the time about 4 years ago or 3 years ago. So I can briefly mention. Okay, so what will be the future CPU micro architecture for many cores? So core pipeline should be most efficient in terms of bits per watt, in terms of bits per silicon, because power consumption is more issue than area, and it should be more discrete pipelines, not, and maybe in-order pipeline instead of out-order pipeline and so on. And MP, you can have different multi-cores, because for smartphones and mobile device, you need DSPs, right? So you can have CPUs, DSPs, and sometimes GPUs. So you have heterogeneous multi-core versus homogeneous multi-core, as you have studied in this class. Okay, and also you can have heterogeneous multi-cores in terms of performance. Okay, you have large, high-performance single core with small multi-cores, because you have to think about underflow. If you have a serial portion, even if you have many parallel multi-cores, you cannot improve performance because it's limited by serial portion. But if you have very high performance cores in the multi-core, you can improve the single sequential portion also. Okay, so maybe another combination is heterogeneous in terms of performance. And the memory architecture for multi-core, you can have shared memory, which is common, and you can enjoy the existing programs running in the multi-core technology also, but it's not scalable because of this interconnect technology, and you cannot use cache to reduce the memory system for many cores because of the scalability issue. You have to come up with directory based cache coherence protocol, which is quite complex and scalable only up to about 100 cores. More than that, you cannot use that technology. So another idea is distributed memory, where we maybe with compiler-based cache coherence management and so on. And shared memory multi-cores are for small scale, dual core, quad core, maybe up to 8 core you can use existing technology, but more than that, you need more fancy technology with high throughput interconnect network, such as 3-dimensional torus. And so people for many cores, like supercomputers, they are working on distributed memory system. multiprocessor. Okay. And another issue was this on-chip interconnect. So we have to go to bus and crossbar will not be scalable to many cores. We need packet switching, point-to-point interconnect. So IBM cell processor use ring technology. Ring is point-to-point interconnect because you can connect one by one. Each transmission line you need to drive only one processor, right? So this is point-to-point interconnect. And maybe for many cores you need 2D, 3D mesh or torus architecture, which was employed in this teraflop machine. This is two-dimensional mesh interconnect. Okay, so maybe more than that you need more three-dimensional or two-dimensional mesh or torus. Okay, cache coherence protocol, bus-based snooping protocol, which I gave you a brief idea, is not scalable, only up to 4 cores or maximum 8 cores. So you need some directory-based cache coherence protocol, which means every cache block you need to maintain which processor has a copy of this one. Okay, and the simplest one is called the full map directory, which has, if you have 100 processors, you have 100 bits. Each bit tells whether that processor owns this, shared this cache block or not. So if somebody writes to that block, then you have to invalidate all the other 99 cache blocks in other processor core, which, as you imagine, is complex. It takes time. It will slow down. And there is other versions of this directory-based cache coherence protocol, but it's only scalable up to about 100 cores. So you need more simplified and flexible coherence protocol because cache is quite important to achieve high performance. And these existing hardware-based cache coherence protocols are not solutioned. And there is other issues if you read papers in the recent conference, because cache can be adapted between private and shared. So by making it private, it can simplify the organization, and some of them can be shared. And you can adapt this area, and there are some papers in that area. And maybe eventually to use cache, you need some compiler or software managed caches to achieve higher performance. And another issue is pin bandwidth. If you have 1,000 cores, each core is asking memory system, and you have bounded by your pins. If you need, you cannot increase the number of pin counts because it will increase your packaging cost substantially. And also so you are limited by number of pins and also the clocking speed of this bus or interconnect technology. Okay, that's called pin bandwidth. Okay, so for many cores you need pin bandwidth of more than 100 gigabytes to 1 terabyte per second, which is quite not easy. Okay, so you are seeing hurdles in that area, and you also need more DRAM. Okay. So pin I/O bandwidth cannot sustain. This is my projection. Multi-cores may work for 2 to 8 processors. Diminishing returns for 16 to 32 processor. It's same as ILP. Okay. But for application with TLP, many core will be a good choice. So main core might be a special case for some special application. It's like single chip supercomputer for that kind of application. And what are the applications? Network processor, network packet processing, they are inherently parallel, so you can apply this many core technology for network processors. And Intel was thinking of these applications, recognition, mining, and synthesis application has a lot of parallelism, so you can apply this technology also. So in the future, I expect this kind of feature. It's a multiple SoC. Okay, so you need to integrate maybe DRAMs will be farther and farther away. Sometime in the future, you need to integrate DRAMs on the CPU chip. Right? And it can improve memory bandwidth and it can reduce memory access latency. Okay, so but for memory expansion, if you include your DRAMs on chip, then that is not sufficient. You need off-chip DRAMs also. Then there is a memory hierarchy in terms of DRAMs, right? So it will be a little complex. Okay, multiple levels of DRAM in the memory hierarchy, and on-chip DRAMs can be used as a cache for off-chip DRAMs, and so on. Okay. And on-chip memory is divided into SRAM and DRAM. And maybe the speed is not so important.Maybe you can replace SRAM with DRAMs and so on. This is my projection. Okay, so you can think just imaginary projection of my future. Multiple system on chip. So you can have CPU with DRAMs, or you can have each CPU have its own DRAMs and so on. Okay, so it's more like discrete memory multiprocessor on a single chip with memory on chip. Okay, and this is an example of Intel's Terascale processor. They have 80 cores in this chip. Okay, so 80 3.13 gigahertz processor, and it achieves 1 teraflops with a single CPU. Consumes about 62 watts of power. And they have 3D stacked memory. So here you have CPU chip, and on the top you have DRAM chip vertically connected, so that each CPU chip can connect to DRAM directly. Provide and this is at each intersection. You can think they have this processor core, and these interconnects are mesh. It's more like a go, right? Baduk in Korean. Okay. And the large challenge: power dissipation, and memory bandwidth, cache hierarchy design, and coherence. And this is actually discrete memory multiprocessor. So each CPU has its own memory, and you don't have to share. So cache coherence problem, there was no cache coherence problem. And they have this packaging terminology, heat sink, on the top, so that you can decrease your temperature and the heat. Okay, and this is the core technology. Each core you have this network of router, because this is two-dimensional mesh, and message passing. This is memory. So every packet, every processor is doing their operation. Sometimes they need to do some communication, right? And then you have to assemble a packet and send it to this router, and it will route to the other processor. Okay. And each processor has its own data memory and instruction memory, and main functional units are actually floating point unit called FMAC. FMAC means it's multiply and add. You can do multiply and add with a single FMAC. And they have two FMAC, floating point unit. Okay. And this is the full photo die of the chip. Okay. And they use 65 nanometer process, A metal, copper, and 1 polysilicon, 100 million transistor, and so on. And the packaging, it has 1,248 pins. So it has many more pins compared to the processor such as i7, because usually they have less than 500 pins, because they have many more cores. You need more chip pin bandwidth to the memory. So the wisdom has changed in the last 10 years. The people think power is free and transistors are expensive, but now, because of power war, you cannot consume more than 150 watts of power. Okay, so the usual maximum is 130 watts. So power is expensive, but transistors are free, because you can reduce the feature size still, right? Regarding power, people think about dynamic power only, CV scale F. But for desktop servers, for high performance, the leakage power can go up to 40%, and this is quite substantial. So you have to consider both static power and dynamic power. And people think you can reveal more ILP via compilers and architecture innovation, but as you have studied, there are not much parallelism in the application. Even if you have 100 issues superscalar, the actual IPC you can achieve is 4 to 5. Okay? And you have diminishing return in terms of finding more instruction level parallelism. And people think multiply will take long and load and storage fast, but we have memory wall. Okay, loader and storage slow, and multiply is compared to memory is much faster. Okay, it takes more than 200 clock cycles to access DRAM, but floating point multiply takes only 4 clock cycles. So on-chip computation is nothing compared to off-chip memory. Okay, unit processor performance will double every 18 months. This is Moore's law, but Moore's law does not apply because of power wall, IAP wall, memory wall. The doubling of unit processor performance now takes 5 years because every year only 20%. Okay? And people so don't bother parallelizing your application because you can just wait and in a few years you will see much faster sequential machines, but that's not true anymore because it will take a while. So it will be very long way for a faster sequential computer. And this is the trend. We will see multi-core with higher throughput, but not single program performance. Okay? And increasing clock frequency is the primary method of improving processor performance. So you thought higher clock speed, high performance, but increasing parallelism is the primary method of improving processor performance because you improve your clock speed because of the power work. Okay? Okay, so I stop here and I ask you to prepare for at least one paper today, right? So who will start first? Any volunteer? Nobody? So I can ask anybody? Okay, so any volunteer? Okay. 5 bonus points for your.
So if I want to present 2 papers today.
No, one paper. One paper, right? So everybody needs to present one paper and then we'll come back for the next phase, okay? So we have 3 weeks for presentation starting from today. So maybe some of you need to prepare for next week, but most of you will present the 3rd week for second presentation. So today I expect you to present one paper. Any volunteer? Nobody? You want to do first? Okay. So I'll give you 5 bonus points. Send me email. Okay. So for each person, prepare for about 20 minutes presentation. Okay? So about 20 slides, not more than that. You cannot present everything. So you have to present at least their idea, intuition, motivation, and their result. Okay? And we start, but I will not go over that much quickly because if I go over that much quickly, you miss many of the concepts that are presented by the paper. So we discuss enough time. But the maximum maybe 30 minutes or 40 minutes. Okay? So what is your name?
My name is Aurangzeb.
Aurangzeb.
Yeah.
Okay, Aurangzeb. Okay, this is your slide?
Yeah.
Not PowerPoint?
This is PowerPoint.
Okay. Oh, I see. Okay, let's look at. So let's look at the title first.
Yeah, this is my first paper, and I will talk on buffer onboard memory system. And this is from Elliot Cooper Ballis from the University of Maryland.
And where was this paper presented?
Is 2011
ISCA.
ISCA. ISCA.
2011. Okay. Buffer onboard memory system. Okay.
So this is my outline. I think I can go next. Actually, this paper talks about the memory system, considering the power and the performance. So at first, the author mentioned about the history of memory memory design trend, and for the at least 15 years, the memory does not optimize for the design consideration. So usually, most of the for a long time we use dual inline memory system, and as you know, the speed is less than 100 megahertz. And moreover, if we want to increase the memory, then we should think about like more DIMM channel. But if we use more channel, it will include crosstalk and reflection, and that degrades the signal integrity. So therefore, people try to we should not increase DMS channel.
What do you mean DMSRL? What is DMSRL?
DIMM,
DIMM?
dual inline memory module.
Yeah, I know DIMMs, right? So, okay. Reduce number of DIMMs.
That means number of DIMM slot. It's number of memory.
Mm-hmm. Usually the PC, there are 4 slots.
Yeah, 4 slot.
Okay. So what you mean is to
Suppose my PC support 100 megahertz with 4 DIMM,
okay.
but I need like one suppose 400 megahertz. Then remove 3 and use on.
So you want only one DIMM with
Yeah.
higher clock speed.
Higher clock speed.
Actually, if you think about transmission line, okay, it's not proportional to the number of DIMMs. It's proportional to this each transmission line connected to each how many chips in DIMM. Okay,
Yeah.
and I'm not sure. Okay, so the actual organization is DIMM is like this. We have 8 chips here and 8 chips on the back. Okay, and the problem of this transmission line is in the address bus line, not in the data bus line.
Yeah. Address
Okay.
bus line.
Address bus line comes in here. It goes to here, goes to here, here. So 8 branches. This increases this reflection and it increases the number of loads. So it actually takes time.
Yeah, it takes
Okay, so this is the signaling issue. Data lines are actually every bit they work in parallel. So you have 8 chips here, 8 chips on the back.
Yes.
So 16 chips, each chip produces 4 bits. So 4 bits wide, 16 chips, they become 64-bit data bus. Okay, so 64-bit data bus and maybe let's say 32-bit address line coming here. And when the CPU access one DIMM, the other DIMMs are inactive. One active at a time. So it's not proportional to the number of DIMMs. What the author is arguing does not make sense in my idea. It's more number of chips that are connected to your address bus line. And people think of each DRAM chip. People are thinking of one-dimensional array, a two-dimensional array, single. But nowadays they decompose into multiple bank to increase parallelism.
Yeah, I
Okay.
think. But if you think about TDMA, like
Okay, so that you can do something about it inside. But here, I don't know. So let's hear about your, maybe. I'm just giving them background. Okay.
Thank you. So one suggestion, authors on things author mentioned that usually people to increase clock speed they reduce number of beam channel. So, but the drawback is like we reduce the total capacity. So author says that okay, if you want to.
So what's the problem and what's the simple solution? Okay, let me understand what is the problem. Problem is signal integrity.
Yeah, problem is signal integrity
And to reduce signal integrity, the author suggests you need to decrease the number of DIMMs.
Yes, because signal integrity means if we have more channel, that means more cross stack.
Right, that's what I said. You need signal integrity comes from number of chips connected to its transmission line, that number of DIMMs. So I don't understand what the author is trying to say there, right? It's not true. Do you understand?
Yeah, I understand.
But do you understand this?
Yeah, I understand.
How do you understand? Why number of DIMMs are important?
Actually, I think about the TDMA, like suppose there are 4 memory DIMM.
Okay.
So suppose if we want to use all memory DIMM, then sometime for this, sometime for this, sometime for this, and sometime for this.
Right.
But if we have only one DIMM, then always dedicated to that DIMM.
Okay.
So in that case, like we don't need to think about like on kind of maxing something max like TDMA.
TDMA, what do you mean by TDMA?
Time division multiple access. Like suppose we have 4 DIMM. So sometimes we access here, sometimes we access here, sometimes we access here. Suppose this. So in that case, if we want to use 4 memory DIMM, then we need like suppose each DIMM take T time. Then we should think about we can come back here after 40 time.
Okay. So
this is all kind of TDMA technique like.
I'm not sure what TDMA technique, but the people actually use for the DIMMs they can use interleaved memory organization with the single address coming to
TDMA
each DIMMs.
is interleave, yeah.
DIMMs, you can actually exploit this, do some in parallel pipeline fashion so that you can improve the throughput, which I gave experimentation to undergrad. You remember, right? But I still don't understand what do you mean by TDMA or whatever.
TDMA is like interleave.
Do you understand what the meaning of interleaving? Interleaving is not just TDMA. It's not TDMA. TDMA is nothing. Do not discuss TDMA. It's not in computer architecture. Because one DIMM is active at a time. That's true because there is only 64-bit bus line connected. And that should be used by only one DIMM at a time.
Okay, I can show you the paper, but sorry.
So actually this explanation is not enough. You need to look at the reference to understand. But you cannot guess. You didn't have time to go over this reference, right?
Yeah, actually I prepared 2 presentations today, so I thought.
I see. Okay. So anyhow.
Yeah, actually author suggests that the summary is like this. Like if you need more speed, okay, use only one DIMM, not more DIMM. So author that suggests. That means this is that. Actually, this is introduction. So he told about based on the history or previous design. So
Okay,
that's all.
let's go over the slide.
So, but as you do that, the clock speed will increase. That means memory access, but we lose the total memory size. So one simple solution is okay. Increase this slot, like not 8, use like 16 and upper side 16. In that case, we can increase the total memory. But if we can do that, we need to use more area. And moreover, to
And this simple solution, another drawback is it's not memory is not expandable.
expendable.
Yeah, so that's practically not used. Anyhow, let's go to the next one.
Then author suggests a fully buffered deep memory solution. Previously, the memory was directly connected to the processor, but now people try to put some buffer between CPU and the memory. So that is called fully buffered deep memory solution, and use a packetized protocol to communicate data. And moreover, we can use like different bus, like from memory to buffer. Maybe there is more data bus, that means more channel, and from memory to the CPU, the number of channel can be reduced for the faster communication.
So actually this fully buffered DIMMs are actually used in commercial systems. What? Okay.
Actually, author proposed the modified version of fully buffered deep memory system.
Okay, so what he suggested this paper is trying to modify existing fully buffered DIMM design a little bit.
Yeah, yeah.
So that they improve.
They improve the performance
Okay,
and the
okay.
speed. That's it. Actually, considering this fully buffered system, there is one drawback, like the high-speed I/O or PMB. It will consume more power and generate more heat, and more thing. This is not cost-effective because they suggest to use AMD for each memory. Like suppose I have a memory, then each memory contains their own AMD. But then IBM, Intel, and AMD suggest some solution. Okay, don't think about the AMD, that means memory buffer for each memory. Only think about a memory bank. Suppose more than 2 or 4 DIMM and one single buffer for the memory bank. So that means we can combine these 4 memory bank and we can use a single memory buffer for this memory bank. And author used that solution from the IBM or Intel or AMD, and author modified that solution and also modify some operation. This is the memory suggested by the IBM, Intel, and AMD. Yeah, as you can see here, like there is single memory DIMM and there is buffer and there is controller, and after that they increase number of memories. That means 2 DIMM here and there is some memory buffer, and in here AMD use 4 DIMM and they use single buffer for here. And this is the system proposed by the author. Actually, this is the modified version of this AMD system. Yeah. They used more than one DIMM, and there is a simpler controller for this bank, and this bank contains some rank, the first rank, second rank, and third rank. And after that, this is the unit, and this unit is repeated here. The data bus is 64 bit, and from simpler controller to the Bob memory controller, buffer on board memory controller, there is a link bus that can be lower than 64 bit or more than 64 bit. And after that, from here there is a cache and there is processor, and this can be also different bit width.
Okay, so this looks like the key concept.
Yeah.
Okay, so can you explain? So you said they are trying to revise or modify AMD design, right?
Yeah, yeah.
Okay. So give us some explanation about AMD first, and then what the author's idea. Okay. Okay, this is AMD.
Yeah, this
okay.
is AMD.
This is what? This is controller. Okay, memory controller.
Yeah.
And what is it?
Memory controller, like there is some bank, like
But what is this one? This is called what? This is buffer?
G3MX.
GCM.
Sorry, actually I didn't go through this paper.
Okay, so compared to the other IBM or Intel, you
Yeah.
have similar structure. So you have controller, buffer, and DIMM. Is that right?
Yeah.
Okay, so for IBM design, you have one controller corresponding to one buffer,
One buffer.
which corresponds to one DIMM. Okay?
Yeah, one DIMM, yeah.
Okay. For Intel design, one maybe many controller, but one controller corresponds to two buffers, and one buffer is responsible for multiple DIMMs.
Multiple DIMMs.
Multiple DIMMs.
Actually, this is the channel.
Excuse me?
Like for the Intel,
Yeah.
like there is one channel and there is another channel. And
Channel. Okay,
Yeah.
channel. One
Yeah.
channel. So one channel, two channels.
Yeah.
Each buffer supports two channels.
Yeah.
And each crossbar supports two buffers. So it's more hierarchical. Okay?
Yeah, hierarchy. Yeah.
Crossbar supports two buffers. Each buffer supports two channels, and each channel supports multiple DIMMs.
Multiple DIMMs.
Okay. Here, the A and B, one controller supports multiple buffers.
Yeah.
Okay. So and each buffer supports one channel,
Mm-hmm.
and one channel supports multiple DIMMs.
The multiple DIMMs. Yeah.
Okay, so instead of this one, author is trying to modify this one.
Yeah,
because
this
he
one.
thinks this is better than this.
Yeah, because there is the memory. There are two memory controller. Like for the Intel,
Okay.
the memory controller is 2,
Mhm.
but here is single memory controller. So
I don't know, but 2 may be it's more scalable. So I'm not sure whether that's the advantage or disadvantage. Okay. And here each buffer supports 2 channels.
Yeah.
Compared to this one, it's only 1 channel. So why author choose this one instead of this one?
yeah, actually I requested the author. So author gave me some presentation file. So if you want, I can show his presentation file.
No, I don't want to see that.
Actually,
I want
yeah.
to- so he gave some answers.
No,
He gives-
yeah, he gave his presentation file. Yeah, because
I'm
actually
not sure. The
in this-
presentation file doesn't mean he give answers. Does he give answers to your
no,
question?
I asked about like your structure. He explained only this structure. That means this is the only picture in the paper. That means that show his structure, his idea. So I said, your picture is not clear. Like we cannot understand what is the difference between. Yeah, I also asked this kind of thing. So he sent me some 3D and colorful picture. If you can see.
Anyhow, so you don't know, okay?
Yeah, I asked like because this is similar, no different from the AMD and your design. So
Okay, I'm just asking. So since it's not clear, okay? So he based on this design, what
Yeah.
he has modified.
yeah, he suggested some data bus technique like 64-bit, and we can increase this bit width, and we can increase or decrease, and we can use some like packeting.
So you mean, okay, let me read. Multiple BOB channels. What is BOB?
Board on buffer. So they said this is a board on buffer channel.
So multiple
Sorry, buffer on
BOB.
board. Yeah.
What do you mean by multiple BOB? Here, it's a single BOB or what? Let's compare with this one and the other.
Like this is a single channel.
Single channel.
Yeah, and author said this is a single channel, but he renamed this buffer on board.
What do you mean by multiple BOB? So this one looks like it has multiple. So is this one different? This one is single controller connected to multiple channels, but this one only single channel. So, right?
Yeah, that means he combined this and this. One controller,
Okay. So let me.
controllers, channel.
So each controller can support a single channel or multiple channel.
Yeah, multiple. Yeah.
I'm not sure what that's the advantage or
So
disadvantage.
actually, yeah, I asked because there is no difference between this design and your design, and so he gave me some.
Okay. Let me. Okay. Each channel consists of LR, R, or UD. What is LR or R or UD?
Actually, I don't know the full name, but maybe there are some different types of DIMM, like DIMM structure.
single and simple controller for each channel. Single and simple controller for each channel. Faster and narrow bus between a simple controller and CPU.
From this to this,
This
They-
is narrow.
then that means less than 64.
This is 64-bit bus.
Yeah, 64-bit bus
And
because
this is,
less than 64. To
why this is this advantage? Why
Ah.
this is an idea?
yeah, actually author says we use packet like suppose from the memory read and
So this is bus, but this is point-to-point interconnect.
yeah,
Is that right?
yeah.
Okay, let's go over this one. How about this? This all the bus or
This they have separate for this is for incoming and this is for outgoing.
right? But is this bus or point-to-point interconnect? Do you know or?
Actually,
We don't know.
sorry, I didn't read the this reference.
So what is rank? What is rank?
Rank like suppose this is rank on, this is rank 2, this is rank 3.
Each
and
DIM
this
is equal to rank 0, rank 1, rank 2, rank 3.
Yeah, that means hierarchy. Rank is hierarchy. Depth of memory. Like maybe
So still, do you understand? I don't know what's the advantage of their architecture.
actually.
It's okay if you don't understand. I'm just
Yeah, actually, yeah, I asked this kind of thing and so he just gave me his PPT. So you can go through. So I think if you see the PPT, then because he put some 3D. So actually, I guess the technique proposed by IBM, Intel, and AMD, he tried to merge all idea like on memory, then on
Okay,
controller.
so he tried to combine the
Yeah.
ideas from IBM, Intel, and AMD
Yeah,
in
and-
its in the paper, in
Yeah.
his paper. So usually combining means it's sometimes good, but I don't think it's good because combining means it's complex and it's not original. Okay, so is this a good paper or what? How do you think?
Actually, this is from ISCA, so I thought, yeah.
No, ISCA is not the same as before because maybe early 1990s or 1990s, ISCA was the premier conference in the computer science because at the time
Actually,
computer architecture was the big, but nowadays ISCA is not there.
Actually, I cannot judge because I am from electrical, so my area is not computer architecture.
So you don't know.
Yeah, actually, I cannot judge. Actually, I am in circuit design lab.
Circuit design,
Yeah.
okay. Intel, there are many circuit designers. So, so I'm not sure whether this is an idea or what.
I also said that kind of thing. So he said, okay, you can see my PDF there. So.
Okay, let's go over other side.
And actually, they also optimize their operation. Like actually, this is conventional architecture, like a request packet. So if there is some request packet, it will decode that packet and decode to address, request type, and data if the request is right. And they also decode the command to the DRAM specific command like this. And there is some command queue and return queue and some response packet. And response packet will contain data and the address of the initial request. Actually, address because here the address that is sent to here and the return that will contain same address, and then the Bob controller can.
So
return
what they are doing is that you need to do some packet processing and
Yeah, yeah.
communication. So they implement or design
Yeah.
for their machines, right?
Yes.
Yeah. That's all. We don't have to go over this.
Yeah. Actually, that's the idea, and I think this is.
Okay, every package-based.
Yeah,
They
package-based.
have this kind of communication protocol. So, okay, let's go over the other. and then they simulate.
Yeah, they simulate.
They compare to what?
Their simulation is two-type simulation. Sorry. Like two experiment. One is limit case simulation. Random address stream is issued into a Bob memory system. That means randomly some address is sent here and some comment. And a full system simulation. An operating system is booted on x86 processor and applications are executed. That means some like practical scenario like this. So actually, my summary is like author try to find the optimum number of rank, like how many dean should be placed here, like this, and how many this kind of channel should be used, and like what should be the, this should be 64, and what should be the link width, that means how many bits should be considered here, like this kind of. So their simulation always try to like this, like optimal rank depth, that means should be between 2 and 4. Because if we see here, like rank depth 1, 2, 4 and 8, so like 2 and 4 and 8, like this is 2 and this is 8. So from 2 and 8, the improvement, like bus efficiency is not that much. So we can say, okay, in that design we can only use 2 to 4 rank.
Okay, let me ask you a question. So here, the link connecting each div, is this point to point or both? Yes.
This link,
Yeah,
this is bus.
both. Okay, so this is an old technique. So they don't use this kind of both technology anymore.
Yeah, actually, this is very conventional, but they try to find the optimum values for this structure, like how many rank should be here. So after simulation, he found that this is rank 2, that means 2 DIMMs, and this is
4 and 8 are about the
yeah.
same, right?
So level 2 should be 400. Like, yeah, that is the optimization.
That's expectable.
Yeah, and this is the link bus, like, and some instruction. That means the link bus should be,
That's point to point, right?
yeah, point to point.
And what are these different configurations?
Like he used 3, like yeah, he used 3 type of DIMMs, DDR3 1066 and DDR3 133 and DDR3 1600. So this is for DDR3 1066, DDR3 1333.
Yeah, okay, how about these? What are these ones?
Like the bandwidth.
This is the speed of the bus.
Yeah, request link bus width and response. This is the request and this is the response. And he also do some like read and write ratio. Like if the read and write ratio is approximately 2 to 1, then the performance is better. Like here, like request is and response is same. So if we go further, like here, that means we can achieve more bandwidth in this region. That means response link should be like more than this is 24, maybe this is 16, 12, 8, 4.
So response bus width should be at least 8 bits wide.
Yeah,
4
8
bits
yeah,
right,
8 bit, and the response link should be 8 bit. That can be anything, like 4 or 24.
Okay, so request bus, narrow request bus is okay, but the response bus is more important, right? Because narrow 4-bit 4A combination is not much different from this high
Yeah,
cost
response. Yeah,
part.
responses.
So why response is more important than request? This is a request link bus with.
Yeah.
This is response with, because the student cannot see it. It's quite small picture. So here, this figure is corresponds to request bus with 4 bits.
Yeah, 4. This is 4. This is
response 8.
Yeah,
So
response 8.
request 4 is quite small. Why request can be small? Well, that's my question. Do you know? If you don't know, it's okay.
Request like this is on like address or some, I guess, address and that means for request read and write. Yeah, I guess, yeah. Suppose request means write and some address. So here author says that read to write, that means if the number of read is more than number of write, right, 2 to 1. So in that case we can get
No, read and write. The
request.
This is different.
response is read, right? On kind of like response, on response should be read and on request should be write.
Right. Write also requires some data going out, right? You
Yeah.
send data. So for write, you need send address and data. For read, you send address and data comes back.
Yeah.
Okay? And so does it explain this request and response?
No, actually
I understand that
it is
read
like-
is more frequent than write.
Yeah.
This sentence says just read is twice more than write.
Yeah, twice
That's
more
all.
than write.
But that doesn't explain request and response ratio in this both ways.
No, that will not answer that question. That answer the bandwidth, like
Bandwidth? I don't know.
suppose that is the height of the pillar.
So anyhow, maybe we can skip. What's this?
This is the link bus. Like this is the bandwidth and this is the bus efficiency. So bus efficiency for the link bus and this is the bandwidth for the link bus.
And which one is good?
So 8 by 8, 4 by 12, request over response. So this is maximum. So 8 by 8, if the 50%, that means one read, one write.
So if the read is from about 40 to 70%, then this 8 by 8 configuration is the best.
Yeah, yes.
8 by 8 means
Request is 8-bit and response
request is 8-bit and
response is 8-bit.
So that's somewhat contradictory compared to this one, right? Since they prefer,
That means they
This
prefer
one.
this,
Yeah,
this,
this
this
one,
one, this
right.
one.
assuming the same, they spend on the same line.
Line, yeah.
Okay, I see.
And this is that means limit case simulation.
What is limit case?
Limit case, that means randomly they generate
Random number.
randomly they
address
generate
generation.
address and they send to the memory system.
Okay. Okay, let's go to conclusion. Let's skip this one. I don't think we can understand all the details because we don't understand the basics. Let's go to the conclusion.
So actually author tried to new memory architecture combining some previous proposed design and it can increase the speed and the capacity like this. and the idea is like intermediate logic between CPU and the memories.
So this is more like performance study of
Yeah, performance
adjusting some design parameters.
design parameter. Yeah.
No new ideas.
No
The
new
ideas
ideas.
came from existing design.
Existing.
They try to combine and they come up with some system that can combine the ideas from existing design, and they don't know the actual parameters for the design, so they do the simulation, and this might be the optimal design for
Yeah,
this
yeah.
kind of assumption. Or
To
this
find
kind
the
of-
optimum values for the
I see. Okay.
Thank you.
Okay, let's have a break and we'll come back.